All right, welcome back. So today we'll be looking at a very common linked list problem. So you may have heard this one before. It's called the linked list cycle. Now this is a relatively simple problem, but the reason why I want to cover this is because uh, the most efficient solution for this is a very common pattern used with linked list problems. So if you understand the pattern that I'm going to use to solve this question today, then in future linked list problems, more difficult problems, you can think of using this pattern to help solve future questions. So I think it's important to know. So, anyways, let's read the description. Given a linked list, determine if it has a cycle in it. To represent a cycle in the given linked list, we use an integer pos, which represents the position 0 indexed in the linked list where tail connects to. If pos is -1, then there is no cycle in the linked list. So the input is 320, -4, pos 1. And the output is true. And the reason why pos is 1 is because if you look, since it's 0 index, it specifies the linked list would be 0 index. 3 is at the 0th index, 2 is at the first index, 0 at the second index, -4 at the third index, and then it cycles back to the first index where 2 is. And so essentially, a linked list is essentially nodes that point to other nodes. And so a cycle in the linked list can be defined as a node pointing back to some other point that we visited within a linked list. And so it just creates a sort of internal cycle. It doesn't necessarily have to go back to the beginning, as seen in this picture. And then similar thing here. The 2 just loops back to the beginning. So yes, there is a cycle. And then, of course, if you just have a single input, there's no cycle in the list. So that's an edge case you should think of. And yeah, the problem is pretty straightforward. So let's just jump into this. Okay, so here I have drawn a cycled linked list. And so to come up with an initial approach, you might be thinking to yourself, okay, well, this should be easy. If I can just modify a list or keep track of nodes that I visited, then if I encounter that node again, then I'd have my answer. And that's certainly one way of doing it. I mean, for every node you visit, you could modify, the value to whatever. In this case, maybe if you wanted to modify it to, let's say, an asterisk or something, I don't know. And so if you encounter the asterisk again, that means that you've, at some point looped back and you would eventually land on the previously modified node. Now, this works, but this all hinges on you modifying the linked list, and most problems don't want you to modify your input like this. So we need a better way. So how do we do this? Well, this all goes back to the technique I talked about in the beginning. So there's a simple way to approach this. And so with linked lists, one technique you can employ is called the two pointers. And so what do we have is I'll just make these two different colors. So we'll have P1 and then we'll have P2. And so P2, the blue one, will move twice as fast as the green one. So the goal here is if there's a cycle, we want both those pointers to match up at some point. So when we start, pointer 2 will explore 2 steps ahead, whereas pointer 1 will only move 1 ahead. And we just keep repeating this. And at some point, it is guaranteed that those 2 pointers will match up if there is a cycle. If there is not a cycle, if it ends at some point, then we know that there is no cycle. So if they match up, there's a cycle. If they don't, for whatever reason, then there's no cycle. So let's just demonstrate this real quick. So we have these 2 pointers right here. And so blue, would move here, and then green would move 1, right? And then blue would move here, green would move here, right? Just to make this, and just to speed this up, so what'll happen next is we'll have blue, and it'll move here, and then green will move here. Again, blue will move here, and oh, look at that, you see, they're both matching. And so when both the pointers match up, then that's how we know that there is a cycle. So again, this is a pretty straightforward problem. There's not that much to it, but I just wanted to put this out there because I want to highlight this technique. And so it should go without saying, but the runtime of this approach is just O of n because we're just looping through the linked lists, and at some point we will stop. So that's not too much of an issue. And then space is O of 1. Um, like with the previous approach, we probably could have used the hash map to keep track of things, but because we're just using pointers, we don't have any extra space. So runtime is O of n, space is O of 1, so this is pretty optimal. So with that being said, let's just go and code this. And so now we're going to write the code for finding a cycle in a linked list. And so first things first, we usually want to start with looking at any edge cases. So in our case, the problem already explains one right here. So if we have just a single node, then we just return false because then there's no cycle. Or also if the head or the initial node is just none, like if there's nothing there, that's another edge case. So in the event that that happens, what do we want to do? Well, we'll just simply return false, right? So let's quickly do that. So if head is none, or head.next is none, return false, right? Cool. And then at this point, we want to establish our 2 pointers. So we'll have a slow pointer, which will just be head. Then we'll have fast, which would be head.next, right? And then fast will move 2 spaces forward versus slow, which will move 1 space forward. And so we could just simply enter a while loop. And so while fast and fast.next, whoops. So the reason why we're saying fast and fast.next is we're saying as long as fast is not null and fast.next is not null, then we continue moving. So the reason being is because since fast is exploring at twice the speed as slow, if it encounters the end of the linked list, then of course we want to just end it there. So yeah, that's the logic behind that. And so all we're simply doing here is just updating fast to be fast.next.next, and then slow is equal to slow.next. So again, fast moving 2 spaces, slow moving 1 space. And then we can just have our conditions. So if slow is equal to fast, so if they both equal each other, then just return true. Otherwise, if we go through this entire list and we don't trigger this condition, then we just default to false. Cool. So yeah, we have our edge case, so that's good. We have our variables, we have our while loop, the logic has been implemented, we have our exit case right here. Everything looks good, so let's just run this and see what we get. All right, so that passes. Now let's submit. Awesome. So there we go. Like I said, this is a simple problem, so don't sweat this one too much, but just really try to understand the 2 pointers because that you can apply to a lot of linked list problems, and it's a very handy approach to have. It definitely applies to more difficult problems, so this is just the start. So hopefully you learned something, and I'll see you guys in the next one.